welcome to today's Research Pays Off. I'm going to hand it over to our speaker, Eric Olson of Solmax, to give his presentation.
Thank you, Lauren. I appreciate it. And thank you, everyone, for being here today. I know, if you're in the northern climate, it's summer construction season, and everyone gets pretty busy up here where we have the 4 seasons. Also want to just say thank you to the members of the National Road Research Alliance. I just think I have a lot of respect for that program and its mission. I know Solmax, we've been an associate member for, 5-6 years now. And we try to regularly attend various meetings, and it's just a great organization. So I appreciate it and appreciate you allowing me to speak here today. So like I said, my name is Eric Olson. I'm a geotechnical engineer, consultant for about 8 years, went into geosynthetics in about 2019. Was a CE officer and the Air Guard for many years and recently retired, and also SCSU Jackrabbit. If there's anyone else on the call, go Jacks. So I'm going to turn my camera off too, just for the sake of bandwidth. Today we're talking about the concept of the 100-year pavement foundation, and that's something that some people have maybe heard in other conferences throughout the years, and how maybe moisture management geosynthetics can play a role in achieving this. So when we talk about the 100-year pavement foundation, we do need to ask how our roads are today and where we are. Currently we do this 20-year design method. Now, I encourage anyone to challenge me on this, but my understanding of the, we got someone unmuted.
I'll take care
I challenge, sure. This idea of the 20-year pavement design and where it came from. And I was always told this came back in the Eisenhower days when we built our interstates, where we have enough money to make our roads last so many years. They can't fall apart right away, but we need them to maybe last at least 20 years. So it's kind of an arbitrary number we picked. And if we look at that concept of the 20-year pavement design, that is under the understanding that we are rehabbing or repairing or doing full depth construction on 5% of our roads every year. I was trying to actually find the data on how much road, what's the total percentage of roads we reconstruct or put in our maintenance every year. I couldn't find that, but I think 5% we're not hitting that 5% target. So the ASE, I'm sure a lot of people reviewed this report card when it recently came out. Our roads were upgraded, we went from a D to a D+, but so we obviously still have a lot of room for improvement. And most of, when they did that survey, they determined that, 49% of our roads are considered either poor or mediocre at best. Or just adjusting the screen here. So today we're going to look at 3 main documents here. The first is the Transportation Research Circular done at TRB on the idea of the 100-year pavement system. The second document is the FHWA Geotechnical Aspects of Pavement. And the third document is testing done at the University of Texas at Austin, the accelerated pavement testing. So first, this circular. So this circular at TRB, starting in around, I believe it was 2023, workshops were conducted at TRB about this idea of the 100-year pavement foundation. And this workshop included around 75 stakeholders. This included people with the DOT, contractors, geotechnical engineers, manufacturers, academics. And in 2024, they published this 68-page circular about what is needed to achieve the 100-year pavement system. And some of those key recommendations included words like sustainability, resiliency. Maybe there are ways we can include unique geomaterials such as geosynthetics to provide more effective solutions. Another one is improving control of moisture and providing more effective drainage in our roadway systems, right? So, and I think a lot of people understand this. And it's also discussed in the FHWA geotechnical document I talked about that, some of our problems with our pavements is in our foundation systems, whether it's the intrusion of subgrade soils or excessive loads or the inadequate drainage of water. And these issues are very costly to us as taxpayers, right? We are paying several $100s a year per as motor vehicle operators due to damage caused to our vehicles from potholes. Repairing potholes is expensive in general, and if you live in northern climates or areas with problematic soils, these costs are even higher. If we look at the annual cost of potholes in our top 10 metropolitan areas, we're looking at $250 million a year just in pothole repair. And this is data pulled from AAA, Seal Masters, and a few other sources. The good news is we actually kind of understand why we get potholes. This is a table within that FHWA geotechnical bulletin, and here we kind of have a cause and effect chart. On the very left, we have some of the, at the very top, we have some of the symptoms that we see, some of the failure mechanisms we see on our roadways. And then on the left here, we have what I would call maybe the root causes of these failures that we see within our roadway systems. Well, we can actually break down these symptoms into various functions that geosynthetics can provide to help reduce the amount of damage we're having to our roads or the amount of failures we are seeing. And these functions would be just separation, reinforcement, and moisture management. Okay. And so since we're talking about the 100-year pavement foundation, we do have this symbolic road to the 100-year pavement foundation we're going to be going through here today as we break down each one of these functions and how they can affect our pavement system. So for, the testing we're going to use to kind of evaluate this is done at the University of Texas, Austin. This is the accelerated pavement testing machine they have there. This is a reduced scale model, 1/3 scale model here. And you can see this pavement section. We have an artificial subgrade with a simulated water table, 5-inch base, and just a 1-inch layer of asphalt. So it is a reduced scale. This machine, the tire loads, it's about a 90 PSI load that the tires are exhibiting on this pavement system. And you can see it kind of has this track, and we can do multiple cycles, right around 7,200 axles per hour is what this can do. And we can look at rutting and things like that. The subgrade is kind of a combination of a clay and sand. I was trying to find the CBR of this in the report. I didn't see exact value, but I know they did try to compact it to a certain compaction level, but a specific CBR value was not provided, I believe. But so these are the 4 test sections to look at here. We have a control, another section with just a separation geotextile, one with a geotextile that can provide separation reinforcement, and then we're going to compound and add moisture management. So we have separation, reinforcement, and moisture management, and we're going to look at the compounding effect of adding each of those functions to our roadway system and what it can do. So let's first look at our control. So running through that accelerated testing, after about 700 cycles, we had about 3 inches of rutting here on that reduced scale section. So that's our status quo. That's what we're doing right now without addressing any of these issues. And to quantify this, we're going to give it a relative benefit of 1. All right. But now let's look if we add separation. And separation, I think, is one of the most underrated things for roadway construction. It is crucial for long-term performance. We don't want our materials mixing. We don't want fines pumping up from above or our base getting pushed below. And, you know, unpaved roads are a great way where you see this constantly. You know, and Jordan and Hicks, they did a study. This is, I think, back in the 80s. Basically, they took 4 different base courses. They slowly added fines. They started around, I think, 5 or 8% fines, but right around 14, 15% fines. The modulus of the base course dropped 50% in everything they tested. So when we have fines contaminating our base materials, the strength of our base materials and their ability to handle traffic loading decreases rather quickly. And I think, like I said, most people understand that and get it and realize once you think about it, it is very important. There's 2 types of separation geotextiles we often see out there. One we would call a non-woven, the other we would call a slit tape. Slit tapes were basically the original geosynthetic developed back in the 50s or 60s. It's basically the same when you buy a blue tarp at Home Depot and put it on your trailer. That's a slit tape geosynthetic. It's really not that high functioning of a material, and it actually causes a lot of issues. Silt fences are slit tape materials. And this ability of them to retain water, not let water flow through, causes actually a big problem. And these can actually create potholes by trapping water, not allowing that poor water pressure to flow through it when you have this dynamic traffic loading. So if you get anything from this is please don't use slit tapes. Even FHWA basically outlines, you know, slit tapes due to their filtration and drainage requirements, they should not be used. So when we look at separation geosynthetics, really we want we encourage the use of non-wovens. So these non-woven geosynthetics, they don't have a ton of tensile strength, and they come in various thicknesses, but they are excellent separators, and they do allow water flow through very easily. So when we apply a separation fabric, in this case, we used about a 4-ounce non-woven. It's similar to the Astro Class 3 non-woven, if you are familiar with Astro M288. It is a rather lightweight one, but still, just adding a simple lightweight non-woven to this accelerated pavement testing, we can see the rut depth is reduced by 1 inch, and the amount of cycles are also increased by 70%. So we have less rutting, and we're allowed more passes by simply having some separation within our pavement section. So, and we can quantify this benefit, and it's basically gives us, improves our performance by a factor of 2 when we look at the relative benefit to this, accounting for rut depth and trafficking increase. So within this circular, if you were to scan through this document, you'd see that they mentioned separation 7 times. So there's people involved in this document understood the importance of that. So here we are, moving along our road to a 100-year pavement foundation. Next, let's look at the orange, our insufficient base stiffness, insufficient subgrade stiffness. This is where reinforcement, the mechanical benefit of a geosynthetic, can play a role. And what is reinforcement? Reinforcement is a combination of 3 things. We've got one is lateral restraint. Some people might call this confinement. We don't want aggregate shifting when we have a wheel load. Also, it provides somewhat of a rebar effect, where we're just adding strength to that failure plane and reducing that bearing pressure, spreading that load over a larger area. And then the third one is slightly more complicated. We call it membrane support or tension membrane support. This really only happens once we have some rutting. It's not a big factor until some rutting occurs. It can get rather complicated. If anyone wants to sit and have a coffee and talk about tension membrane support, we can. But we're looking at lateral strain and being able to reduce bearing pressure are the primary mechanisms in providing some reinforcement. And reinforcement is necessary. Now, these are extreme examples, right? But we do have challenging soils all over the country, and we see it time and time again. And we just simply can't over excavate these materials, and we can't put in 4 feet of rock everywhere. While these might be kind of extreme, you know, these are some more practical cases that we see on roadway construction projects where we just have challenging soils to deal with. And so Solmax, we use what we call a high-modulus double-layer geosynthetic. Now, that's kind of a mouthful. I'll kind of explain what that is. Basically, what a high-modulus geosynthetic is it has high tensile strength, or I should say high strength at low strains, which is key. One of the things, though, is strength isn't everything. It does matter. It's a very important part of the reinforcement mechanism, but you still need to have water be able to flow through the material, as we demonstrated with the slit tape fabric. Also, and with traditional geosynthetics, and this is a twill weave. This is kind of the next evolution from slit tapes as developed in the 80s. These are good, reliable products, but to make these stronger, we have to add more yarns, and the opening sizes do get smaller. And then we start trapping water again, which becomes a problem. In other areas, there might be products that actually make these openings bigger to have higher flow rate, but then we start sacrificing our ability to keep fines out as well. Additionally, they're still rather flat, not a lot of surface area to engage the aggregate. Where the high-modulus double-layer weave, it's a different type of weave with more surface area that allows for more engagement with the soil particles, and we actually can make this product stronger without affecting the flow rate. So what that kind of looks like on a tech data sheet, you know, everyone always looks at strength right away when they look at technical data information, and it is important. I don't want to minimize that. But really, when we're looking at geosynthetics for roadway stabilization, we can't ignore the permittivity or flow rate or pore size distribution, and also the coefficient of interaction, which is a measure of friction, basically. AOS, I don't want to use the word outdated, but it is not an accurate measurement of a material's ability to retain fines. We encourage people, just like how soil has a gradation curve, geosynthetics have a gradation curve of their opening sizes. So pore size distribution better represents that. A good number to look at is the 050 value. So 50% of the openings are 208 microns or less. So there's this balance of having very small openings, but enough of them to have a high permittivity. And that's really what makes a geosynthetic perform well when we talk about stabilization, reinforcement, and separation. In this case study with the University of Texas Austin, the MIRFI RS580i was the double layer weed product used for testing. It was tested in the Montana State Western Transportation Institute. It kind of confirmed everything I just said about being able to perform all these properties, made it the best performing geosynthetic in this case study. And so that said, when we incorporate this high-modulus double-layered geosynthetic, we have separation and reinforcement combined. And we could see here the rutting, very similar to just a separation, but now we have over 6,000 or 6,400 cycles before we achieve that rutting. So half as much rutting, almost 8 times as many passes as the control. That relative benefit, now we're bringing that up to almost a 25 compared to our status quo as we quantify the improvement of rutting and traffic performance. Going back to the circular reinforcement, mentioned 8 times. So once again, this is something people understand is an important part when we talk about our 100-year pavement system, 100-year pavement foundation. So, and that brings us a little bit closer to that 100-year pavement foundation, but we still have 3 issues on this chart we haven't addressed: moisture drainage, freeze thaw, and swelling. And these are all, in fact, moisture issues. Also, if we look at the other 2 in orange, base stiffness, subgrade stiffness, moisture actually impacts these too. So these are all, when we look at these 6 conditions, 5 of them can be influenced by moisture. And that is the critical piece of the puzzle here to get our long-term 100-year pavement foundation, is incorporating moisture management. So some of you may have seen some of these quotes before, but you know, Munich Budu, who wrote a textbook on soil mechanics, you know, he always estimated that in undrained shear strength of fine-grained soils can increase about 20% for every 1% reduction in moisture content. And we're going to come back to that, but it's a good number to undrained shear strength. 1% reduction, you get an improvement of 20% in undrained shear strength. Harry Sedegren, author of Drainage and Highway, Airfield and Pavements, you know, he also estimated that pavement surface life gets cut in half if your road is saturated just 10% of the time. Pavement life cut in half, just saturated 10% of the time. So both of these people understood the importance of adequate drainage in our roadway systems. So this is a project done at the University of Alaska Fairbanks. They wanted to test how moisture impacted base course materials. So they have a aggregate base course here, and they run modulus testing on it at different moisture contents. The optimum moisture of the material they tested was right around 9%. Just reducing the moisture content 2% below optimum, it increased the resilient modulus by a factor of 3. When they looked at permanent deformation, that also increased, or that decreased by 40% just by decreasing the moisture content 2%. Now, if we look at, we go the other way, what if we go 2% over? And I kind of just gave you a preview of that for a second there, but just increasing the moisture content 2%, the permanent deformation increased by 400%. So just kind of confirming what those 2 textbook authors wrote. Moisture damages our road. It reduces our aggregate material's ability to handle the stresses quite significantly, and it really doesn't take that much. So this is one of the projects done, you know, in partnership, you know, the National Road Research Alliance over on Min Road with Michigan State, Texas A&M, and with Dr. David White and NGOs. We had there's a test section out there. This is on the main line, not on the low volume road, where we can see how moisture actually behaves seasonally. So it might be a little hard to read, but we got a rather thick asphalt surfacing. This was in partnership with, I think, the Flexible team. They were doing perpetual pavement research. So we got about 8 inches asphalt, a little bit more, almost 10 inches of base. And then this is 12 inches of sub base. These squares here are moisture sensors, and we have the no geosynthetic here, but we do have, this is where the interface of the geosynthetic, of the subgrade and sub base is. Where this red arrow is, we're going to look at this moisture sensor right here over an 8-month period. So as we can see, this dotted line, this is the initial moisture content from installation. And in this control section, 20 inches below this subbase, we can see how the moisture fluctuates seasonally over an 18-month period. Now these big dips, this is winter right here and here, so we kind of ignore those. But it regularly kind of goes up and down that initial moisture content at installation. Now, if we add a moisture management geosynthetic, and the brand name of that for Solmax is our Mirify H2RI, I'll kind of throw those around interchangeably. That was part of this research project, is having the test cell right next to it. They built the exact same pavement section, but adding a moisture management geotextile right at that subgrade interface. So we're going to look at that exact same sensor, the sensor in that exact same position. We have our control, how our seasonal moisture changes, and obviously, you know, here after winter, we have spring melt increasing that moisture content and probably some rain events here. Using a moisture management geosynthetic, we keep that moisture very, very low. It's other than this weird little spike here, it never goes above that initial moisture content. And that's what moisture management is getting rid of that excess moisture in our pavement system. So adding moisture management to our accelerated pavement testing. So we have separation, reinforcement, moisture management. We reduced that rut depth anymore, but now we're up to 4,600 cycles. So half as much rutting, 20 times as many axle passes. So this is the compounding benefit of moisture management. And when we quantify it to the relative benefit, we're up to about 99 here when we quantify that in this example. Something else that was pretty interesting from this study is they looked at aggregate displacement horizontally. This might be a little bit of a tricky chart to read, but this center here is the 0 is the center of the wheel, and 100 is the edge of the wheel in that testing apparatus. So the darker red it is, the more horizontal displacement. And here you can see the control, the separation reinforcement, and then we add moisture management. And just to highlight, look at the difference between separation and control. Quite a big benefit just adding separation, but even continued benefit between the two. The control didn't even make it to 1,000 cycles. So this is just at 1,000 cycles for the other three. When we take it to end a test, you can see a much larger disparity in difference. Here, the separation, they had to end the test at around 1,200 cycles. Adding reinforcement, it looks worse, but they went to over 6,000 cycles here. And then when we add that moisture management, we see very minimal aggregate displacement horizontally at the same between the reinforcement separation and adding that moisture management. This is a big change right here, just by helping remove water. So let's look at the circular one more time. We talked about separation 7 times. They talked about reinforcement 8 times. Moisture and drainage, that was discussed 243 times. So I think many engineers out there recognize how much of a problem this is in our roadways. And if we don't solve this, we cannot get to that 100-year pavement foundation. And moisture management might be one of the keys to get there, okay? So that's kind of the first third of this presentation. The next, I do want to talk about what a active moisture management geosynthetic really is. And I want to emphasize active, right? Because this is the active removal of water. So first, I want to talk about how does roadway drainage work today, basically. So we construct a road and eventually moisture infiltrates our roadway system, whether it's through rainwater, cracks in the surfacing, capillary water, maybe we have a lot of flooding events. And currently, the way we handle this is we crown the road, or maybe we have ditches and maybe a drainable base, maybe we put in edge drains. These all rely on gravity-based drainage, right? And the reality is this only works when basically our roadway is saturated. The moment it's below saturated, these systems don't really work very well. Or if they do, it takes a really, really long time. So this is, I know we got some very smart people on this call, smarter than me, but this is how I explain roadway drainage to my 7-year-old who is very interested in what I do all of a sudden. And this is my AI generated image, and you'll notice the handle going through the bucket here. So just there'll be some weird disparities between these photos, but how I like to describe it is we have moisture infiltration, and this is just a bucket of sand. And if we just saturate this bucket of sand with water, you know, this is a saturated condition we'll eventually have. We keep adding water. And if we put holes in this bucket, that water will freely drain, even in our granular materials, right? It will free draining to a certain point. Eventually, this drainage will stop. And these holes in the bucket, this represents putting in under drains, crowning, our traditional systems I just spoke about. But the reality is this drainage will stop. And what we're left over is we're still left over with a significant amount of moisture in our aggregate materials. So, and the holes of the bucket magically disappeared when I had AI do this for me. But anyways, I think that's a concept a lot of us understand is the only way for this water, if we have this in a roadway system, the only way for this moisture to be removed is really through the water vapor diffusing across our aggregate layers and maybe evaporating in our ditches or edge drains, which takes a really, really long time. And it's really not effective when we dip below saturation. So that's why we want to provide a new pathway for moisture. And this is with moisture management yarns. So in the moisture management geotextile, we talked about in that rutting study, just for the accelerated testing, this was the product that we use, the HRI. We have two types of yarns in this. So this still has that double layer weave that I mentioned for that mechanical bevelment. These black yarns are polypropylene in that double layer weave. This gives us the mechanical performance we want. We still want separation. We still need tensile strength, and that's what the black yarns do. But the moisture management yarn are these blue yarns here within this geosynthetic. And these yarns are hydrophilic, meaning water is very, very attracted to it and wants to be absorbed into these yarns. So like I said, two components, moisture management yarn, black modulus yarns. And these yarns are very, very tiny. And that the size of them matters because what it does is this causes a capillary suction within the material. So kind of just an image to show how it absorbs within these entanglement of yarns, and then capillary action draws it along the length of the yarns. So what this does is this is not traditional gravity drainage. These moisture management yarns are engineered to actually absorb moisture, pull it, provide suction pressure from above and below. Capillary action will draw it along the length of these yarns, and it will remove it completely from our roadway system. Okay. So just to demystify how this works a little bit, talk about the science of it, and I think this might be one of the more important slides to understand, is it really is about humidity and suction pressure. So one of the things about it, to remove the water, is you do need to have the geosynthetic exposed to a drier area. You would actually, if you brought it down the ditch, you'd maybe cover it with some topsoil and a little seed, some topsoil and vegetate it. That actually works really well. You're kind of watering the ditch or gravel. You really want to protect this edge just for mowers and sunlight. But you do need to give the water a place to go. Another option is you might put this into an edge drain. That has been very effective. And there's all sorts of ways you can maybe daylight this. But anyways, what's going to happen is these yarns want to absorb the moisture. It's going to absorb it from above and below. Capillary action is going to draw it to this drier area, and the yarns will actually evaporate the moisture within them, and then that's going to continue to pull more, and it'll go to these edge and evaporate, and it actually might even drip out of the end. If it's very saturated, you might get a siphon effect to drip out of the edge, and it's going to keep doing this continuously until the humidity balances within the roadway system. It's not going to get everything bone dry. It does have a limit of how much moisture it can take, but what it's going to do is provide a very uniform moisture condition across our roadway, where without this, we'd probably see drier shoulders in the winter than the center, and we have a very ununiform roadway system. So that's how that works in a nutshell. Just a little video to just kind of demonstrate how this works. You can see we have a strip of the moisture management geosynthetic in this little petri dish. We add some just dyed water, and you can see it pulling that moisture slowly across the length of the material there. So this video was actually 5 minutes long. It's sped up, and this is only about a 6-inch strip of material. I like to explain that because this is not a storm drain replacement or anything like that. This is a slow process, but it's a continuous process that goes on until we have that humidity equilibrium I mentioned. So when I talk about active moisture management, what we really want to say is the continuous process of controlling and removing moisture. That is active moisture management, and that's the difference between, and that is not what drainage necessarily is. So we talk about active moisture management, we think of 3 key components. Being able to remove water from unsaturated conditions, having a zone of influence, and being able to pull moisture up a gradient. So we're going to break these down a little bit. Pulling from unsaturated conditions. What do we mean here? We mean, like I said, back to the bucket of sand, when it's saturated, it drains. And when it dips just below saturation, we have an unsaturated condition. And we want to be able to continue to pull moisture out of that unsaturated condition. So University of Alaska Fairbanks, they did this is called the silt column test. This is just an 8-inch tall mold with a saturated silt and basically saturated silt, excuse me. And they basically had this column. They put it on top of 4 different geosynthetics and wanted to see how effective gravity was in draining the geosynthetic. So this is maybe a little confusing chart, but here we have the height of the column, and this is the moisture content. And this is the moisture content at each inch along the height of the column. And the saturated condition was right here at around 53% in the saturated silt. So what's really interesting is all 3 of these other non-moisture management geosynthetics kind of were very similar. Like I said, they did have some drainage, but then they hit a point where negative pore water pressures or suction wants to hold it in, and the silt doesn't want to let go of that material anymore. We'll talk maybe a little more about that later. But the moisture management geosynthetic, the H2R I tested here, was able to pull an additional 3 to 4% more moisture out of the saturated silt along the whole length of that column. So this helped demonstrate, and there's more to this, I believe, this demonstrated the ability to actually overcome that suction forces the silt was applying to the moisture, and the ability to continue to drain moisture out in an unsaturated condition. So there's only 3% less than the other products, but now what we're seeing is we go back to our Voodoo quote, we're improving that silt modulus by 60–80%, the shear strength of that silt by 60–80% just by reducing that moisture content 3 to 4%. What about zone of influence? I said it can pull moisture from above and below. So how do we know that? And I don't have great pictures of this, but this was done at University of Kansas and Missouri University of Science and Technology. It's a very similar thing where you had a column here. This is an aggregate base with various moisture sensors. And we tested 2 geosynthetics. They're identical geosynthetics, other than one had the moisture management yarns and the other one did not. And basically what we saw is there was an effective zone of influence up to 10 inches above the moisture management geosynthetic, where it was continuing to lower that moisture content, where the other one did not. So we know it effectively pulls down moisture up to 10 inches above in this case. A project done near Dallas-Fort Worth with Texas A&M. We want to understand the diffluence in a highly expansive fat clay. So there's a little test section here where they did an additional lane widening here. This is kind of a busy diagram, but in one half of the lanes, we installed moisture sensors, moisture management geosynthetic. They had 2 test sections and 1 control. So the control, no moisture management geosynthetic. They use standard base course, or they call it flex base, I think, in Texas. In the 2 test sections, they used the moisture management geosynthetic, had all these moisture sensors. One of them, they used the same flex base as in the control. The other, they actually used 100% wrap, which I think is pretty interesting. We'll show you here in a minute. So overall, now mind you, this is a fat clay. This is the reduction in moisture content over just the course of a few days here. I think that, as you can see on the timestamp, just 5 days. Moisture sensor 6 had the greatest drop, but this was right by the shoulder. So we kind of ignore this one, even though it looks really good. We're really looking at all these other moisture sensors here. Particularly we want to look at moisture sensor 1. This is the furthest down, 18 inches below the material, the moisture management geosynthetic, and further in, furthest away from the shoulder. And even that moisture sensor 1, we saw about another 2, 3, 4% decrease in moisture content over these few days here. That's 12 inches below the material. So even an expansive clay, a material that wants to hold water, it is still slowly pulling moisture out. And so we can say we do have a zone of influence up to 12 inches below the material. And this will always depend on the material, but I would think expansive clays would be the most challenging one to do this in. And just for FYI, like I said, they had 2 test sections, one with wrap and one with standard egg base. The egg base, they saw 75% less permanent deformation. In the wrap, they saw 35% less permanent deformation. These moisture management yarns actually work really well with recycled asphalt as far as lowering moisture content. Wrap is actually hydrophobic. It wants to repel water, and you have something that wants to take in water. So it works really well and helps give us less permanent deformation. I know wrap is a very common thing right now. A lot of people have it all over, and it's a very great way to reuse materials. So the last part here is the gradient. Can we overcome a negative gradient? So this is another test done at the University of Texas Austin. We have a reservoir here and with a little speed bump. Here's the moisture management geosynthetic, and here's the non-woven strip. And as you can see, moisture moving across this moisture management geosynthetic has no problem pulling water up and going over the speed bump, right? But other geosynthetics, you know, non-wovens do provide drainage, right? They can allow water, but it's just gravity and it can't withhold that moisture. And when we have this little speed bump with a non-woven geosynthetic and we hit the speed bump, it all spills out. And why this matters is especially if you have a clay subgrade, is if you have a little rut or a low spot in that subgrade, moisture can collect there and not drain. Moisture management geosynthetics can actually pull that out and get it out of your roadway so you don't have a future pothole there. So these are kind of the three things that we use to define an active moisture management geosynthetic. If it can't do these functions, it's really not the same thing. So one question is, how do we measure moisture management? It's kind of an abstract thing. And you know, Solmax we're kind of on the forefront of pioneering moisture management geosynthetics. So the reality is these things didn't exist and there weren't ASTM test methods to kind of quantify what they could do. So one of the first things that Solmax came up with is coming up with a wet front movement horizontally and vertically. If you Google this ASTM C1559, this is actually an ASTM for wicking of moisture in aircraft insulation. It's not meant for geosynthetics, but nothing exists. So we actually had to modify it. And it's a very simple test where you actually just put it in a water bath and you lay the geosynthetic completely flat and see how far it brings the moisture over a certain amount of time. And we could do the same thing vertically, you know, and we see here, we can get up to pull water up to 6 inches vertically in this case, just soaking in a bath, right? Not the perfect test, not engineered for geosynthetic, but still it's low cost, easy to do, and does give us some information. So some other things working on right now is, one thing is the vertical capillary rise test. This is something we're trying to maybe get to become an ASTM. Very similar to the other one. The other one is just kind of a visual test, trying to see the moisture rise up. Watching water in it can be very difficult. This is a smaller test, but we have pins here and we take a micrometer and we measure the change in voltage drop as the water rises up through the moisture management yarns over a period of time, and kind of can give us some information about that. The other thing that's very important is moisture management yarns need to be hydrophilic. And this is kind of a pass or fail test, but some people might be familiar with the contact angle. If water has a contact angle less than 90 degrees, that means that material is hydrophilic. If it's greater, it means it's hydrophobic, right? So when you go put Rain-X on your windshield, right, that is a hydrophobic material and it causes water to bead off, right? This is the opposite of that. And this is just a simple evaluation of, can the material want to absorb moisture. The next thing that is kind of new and I'm really excited about, I am still learning about soil and water characteristic curves, for full disclosure. But this might be one of the best ways to really evaluate how well it can actually pull water out of different materials. The previous tests were just like, can it pull moisture or not? But the other part is, can it actually pull water out of soil and aggregate materials? So some people might be familiar with soil and water characteristic curves. These are really just curves that depict the ability of the soil to withhold water under unsaturated condition, and also correlates to unsaturated hydraulic conductivity. And we kind of have three boundaries. This is just a generic curve, and ignore this dotted one. This is a wetting curve. We're looking at the drying curve. But we have the boundary effect zone, and by boundary effect zone, this is where gravity can maybe help drainage. This is the bucket of sand again with water draining out. But once that natural drainage stops, we start entering this transition zone. And then third, we have this residual zone. And the residual zone is where larger amount of suction is actually required to remove additional water. So on the bottom here, we're just looking at how much suction pressure is required to remove water in these unsaturated conditions. And the key thing here is we have this inflection point, and we draw a tangent on this inflection point with a horizontal line from the saturated condition. We get a value called the air entry value, okay? And this is the amount of pressure that is required for air to enter the material at, you know, this certain moisture content when we're just get past this boundary effect zone, if that makes sense, okay? So Just like there's soil water characteristic curves, we can have geosynthetic characteristic curves. And this is what it looks like for our H2RI moisture management geosynthetic. And this curve looks slightly different. We actually have two air entry values. And why is that? Is that we actually have two types of yarns. We have the black yarns, the polypropylene, and the moisture management yarns. So their entry value is actually very low because in that double layer weave with the black polypropylene yarns, there's lots of void spaces that air can easily enter under very low pressure. But at a certain point, the moisture management yarns are actually still wanting to hold on to that water. And they want to hold on to that water until we reach 254 kPa. That's when that's when there's enough suction to maybe pull water out of that. Why that matters is we can compare this to our, like I said, here's an example of a non-woven, which is all polypropylene, and you can see it doesn't take much pressure at all to pull water out. But we also can compare this to geomaterials. Clay, like I said, has a high affinity for water. It takes a lot of pressure to pull water out, but it can be done. Sand more easily can pull water out. Same thing with some silts, and then we can look at gravels. And these are kind of generic curves. Every soil you encounter on site would have their own characteristic curve depending on the combination of the materials, right? But what matters is this kPa, while these materials can have different curves, this is a constant because it's a manufactured product. And this air entry value for the moisture management yarns will be a constant 254 kPa as long as we maintain high manufacturing standard practices, right? So this could be a benchmark on a tech data sheet that we can use to say how capable a moisture management geosynthetic can pull moisture out of our geomaterials. And it can actually be used to help maybe quantify how much we can pull. So if we look at the air curve, if we just match that 254 kPa on the silt characteristic curve, we can compare that to its saturation level, and we could say, in theory, we could pull up to 10% below saturation in this silt. So this is a way we can quantify how much. So if we took less yarns out of our material, this value might decrease, and we'd be able to pull less water out, right? Run the same thing with clay. Clay wants to hold in the material, but here in this example, we can maybe reduce it up to 4% using this soil characteristic curve, which we kind of saw in that other case study down in Texas. Okay. I see 15 minutes left, and we're going to fly through some of this. I do want to talk a little bit about designing with geosynthetics. Not diving deep in this at all, but the big thing here is there are guidances on how to incorporate geosynthetics in pavement design. This is under AASHTO R50, but the big thing here is all methods really are geosynthetic specific. Unfortunately, there's no way to look at a tech data material with moisture management yarns or not and incorporate that into roadway design. FHWA says the same thing. Product-specific studies need to happen when you incorporate geosynthetics for structural betterment and pavement design. We worked with the University of Kansas to develop incorporating moisture management in AASHTO 93 flexible pavement design. We did this, they did this by developing what we call a hydraulic improvement factor in HIF. This GSC, this is a geosynthetic structural coefficient. Any geosynthetic can get tested and determine the structural coefficient that gets applied to that reinforced layer. Like I said, but that is product specific. And even if they have similar tech data sheet, every product, if they're being put in design, should develop their own structural coefficient. This is not a static number either. This is actually kind of a curve, depending on the conditions. HIF as well. Every product should have their own HIF value. HIF is not a static number and actually will depend on where you live. If you're in drier areas with less rain events, you have a higher HIF. If you live in a place where it's ground's frozen for 4 months out of the year, you have a different HIF. So we have done this, not diving deep in this right now. I will say, you know, everyone's moving to ME design methods, and I think we'll have some really exciting news on how we're working with that. Maybe that'll be another presentation here in the future. But just real quick, other projects. This is Dalton Highway. I'm going to just kind of speed through. This is our first install back in 2010 with a moisture management geosynthetic. This basically had frost boils every year they had to replay. This is a heavy truck traffic oil and gas road, and they want to find ways to solve it. Here they have the moisture management geosynthetic. All these moisture sensors here are the squares, big uphill slope. Everything's just draining to the east side. And they actually brought this up because they don't want to suck water into the road. So you can hear significant rain event after construction. And we can see dark reds saturated, dark blues frozen up here, temperature, moisture. After that rain event, this is in September, we do see some drying here just 2 weeks after the fact. Winter arrives, absolutely no saturation in the upper 4 or 5 feet at once winter arrives. And that spring, very little no saturation whatsoever seen in that upper 5 feet as well. And ultimately, that was the first year they didn't have any frost boils on this road. This is the May, that first spring, and they haven't had, I don't think, frost boils yet on this stretch of road. This here is a solar-powered satellite computer. We have 10 years of data of instrumentation from those sensors now, and it's really just doing the same thing over and over again. They actually installed more on this same stretch of road. This is not where the geosynthetic is. This is where they had actually used shot rock and non-wovens. But here, you can see the moisture management geosynthetic. Another expansive soil study, I'll just fly through this. This is the lane widening project. Here they installed the moisture management geosynthetic, and they measured the change in moisture content with these moisture, and they used some different products here. The big thing here is the annual change of moisture content didn't exceed 2.5% where they had a moisture management geosynthetic under. This is also an expansive fat clay, whereas the fat clays in the other places, the seasonal moisture change varied up to 8%. And overall, this is the only section that had no cracking after a year. What's neat about this is the water's not even being removed. They actually just buried it, and it's balancing the moisture across the road. That's not taking it out whatsoever. I do want to talk about the Min Road project one more time. Just a few neat profiles here. So this is just kind of a heat map of moisture of the control and the moisture management geosynthetic. This is that same moisture sensor I showed you earlier, 20 inches below the surfacing and the subgrade. And you can see a big difference in moisture content throughout the pavement. This was taken a snapshot during the spring of 2023. David White did a bunch of lab testing as well. I encourage everyone to just maybe go through the report. He simulated freeze thawing and did rainfall simulation and took a lot of water out in these examples. But if you go to the National Road Research Alliance website, if you go down the geotechnical team right there, you can see a bunch of the results from this research. Great information. The final report isn't out yet, but I think it'll be out this fall, I hope. So there is this, we do have this tech brief that's available. What's nice about this is this summarizes over 35 different research projects. It's just kind of, it just kind of goes, we've done over several research projects over the years, and this is just kind of a desktop review of all those and gives you kind of the cliff notes of everything. It's about 13 pages or so. If you guys want this, let me know. The Min Road is not on there, and that accelerated pavement testing I showed earlier is not within this tech brief, but a lot of great information. And if you see any research papers cited in this that you want the full copies of, please reach out, and I'm happy to share that with you. Just want to share some quick examples, then we'll be done here. This is in Norman County. They use moisture management as an alternative to chemical treatment. Portland cement has gone way up in price, and this was an option that saved them significant money. Here on the right, we can see the daylighted edge here. This is the road. They actually did pave it the next year. You see water in the ditch. This is up in the Red River Valley, lots of flooding. So this is the daylighted edge right here, and you can see how the soil is a little bit darker there. That's moisture being pulled from the roadway and brought to the edge, helping water that seeding I just kind of destroyed a little bit for them. This is just a fun unpaved road in McCook County. We've just had a roll to spare that we couldn't sell on a job. And so we just put it in a spot on a rural county road. Just grain trucks and tractors drive this road only, but we can see a big difference here in the moisture content. If you want a little better view, I have this pink flag that I put in 3 years or 4 years ago when we installed it. And you can see a clear line of where the geosynthetic starts and where it stops. Kind of interesting. One of my favorite projects up in Canada, this is kind of one of my last slides here, is just, this is a job up in Canada, 100 feet of road. They decided to put the edge of the moisture management geosynthetic in a PVC pipe. I don't know why they did this. It was a pain, I'm sure. But what was really neat is you could see the water draining in that pipe, and they actually brought it out to a nearby stream. So this is 100 feet of road, the water constantly being removed. So I work for Solmax. The product is NRRA. For us specifically, our product we've installed all over the country, all over Canada. It's been around since 2010. We are very familiar with how our moisture management geosynthetic works and its capabilities. Every place is a little different, but I think every place it's the same as far as removing water only helps the performance of our pavement. So just some key takeaways. We need to do better on our roads. They're just having heavier traffic and more traffic, and we're not keeping up. And we need to stop doing this, keeping with the status quo. And these are the things we can agree on to help improve that. Both separation, also reinforcement, and then controlling the moisture. Showed you several testing for moisture management and some real world applications. So I do want to just show this last slide once again. You know, as I previously said, we really have a pretty good understanding of why our roadways fail. And we do have a solution to solve some of these root causes. You know, our surfacing will always fail at some point, but if we can extend our maintenance cycles, reduce times between full depth repairs, and be able to allow our roads to handle more and heavier loading, I think we can have a lot of successful, maybe get that D plus to at least a C or a B, you know. So with that, I want to say thank you again. Thank you, Lauren and Raul, for letting me speak today. And I guess now we can open the floor to some questions here. I don't know if anything happened in the chat. I wasn't looking at the chat.
Yeah, there was one question, but it looks like Daniel answered that. So if there's any other questions, if anyone would like to raise their hand and chime in, you can unmute yourself or type it in the chat. Still have a couple minutes to get through any further questions that anyone might have. Glenn asked, have you calculated EPDs for your product?
I don't know, Renee or Daniel, do you guys have any comment on that at all?
Yeah, we are in the process of doing the EPD program. We started it about a year or so ago. There's a slight pause, but we are progressing on that.
I've got a question. This is Randy West at NCAT. So I think, Eric, you mentioned that the main material used in the geotextile was a polypropylene. Could you explain why you chose that particular type of material? And then you didn't say, I don't think, the type of material that's used in the wicking filaments.
So yeah, polypropylene, that's pretty standard for all roadway geosynthetics, like any non-woven geogrid. That's, you know, other products you might see polyester or polyethylene, but polypropylene is kind of the standard. It's inert, doesn't really degrade or anything like that. Like I said, it chemically inert. Like I said, UV light is really its only kind of weakness, so to speak. That said, as far as the wicking geotextile, you know, that is a modified polyester yarn, and I will say that's kind of proprietary information on how it's modified, so to speak. But does that answer your question?
Yeah, it does. So just to follow up real quick, is that polypropylene all virgin polymer?
Yes, we do put in some recycled. You know, in the manufacturing process, there's a recipe, and we want to maintain, you know, polypropylene. The more times you recycle it, the less performance, I guess, you get out of it. So we do try to recycle up to 10%. But yes, it's mostly just virgin, and it is a byproduct of, you know, refining oil, create gasoline. Renee, do you have any more comments on that? Did I say that well enough?
Yeah, I can just a little clarification. So when we talk about recycled, the 10%, we're not talking about post-consumer, because the issue when you start bringing in secondary materials from other sources, all these products are made through an extrusion process, and the extrusion process involves heat and pressure. And if you start bringing in more and more contaminants from an uncontrolled source, then the manufacturing process becomes much more difficult, especially with these high-modulus woven geosynthetics. So, you know, oftentimes what we tend to look at is we look at materials, you know, that recycled percentage, it's controlled, and it's quality controlled from that aspect, because otherwise, you know, from a manufacturing perspective, the last thing we want to do is to damage and gum up machines, and all of a sudden, you know, we're out, you know, offline for extended periods.
All right, thank you.
I see a comment about clogging from Pat. Just to address that, we actually have done testing on clogging for silts and clays. I didn't discuss that today, but we actually, I don't know if it was what university that was with, but we actively try to jam in silts and clays, and we saw maybe a 2% reduction in flow, really just in the outer parts of it. We're not really concerned with clogging too much, especially, while there is dynamic loading that happens, I think it'd be pretty tough because the yarns are so small where there might be some clogging on the outer parts, but not really in the inner parts of the bundle of yarns, if that makes sense.
It looks like Deepak has their hand up.
Thank you.
Oh, yep.
I have two questions. Okay. The first one is, we are looking for 100 years pavement base, right? And the material you are talking about, this wicking geotextile, can that last 100 years?
So short answer is yes. So like I said, polypropylene and both polyester, when they're in the ground, they're really inert. I think the only issue we would maybe need to look at is for some reason you have extremely acidic soil conditions, but they, they are basically a plastic material and won't degrade for a really, really long time. And like I said, unless exposed to like UV light. But they don't shed microplastics or anything like that because they're just in the ground. So yeah, we know the properties of these materials and other applications very well to understand that within our geomaterials they'll last a really, really long time.
Thank you. And follow-up question is, you have shown that you doing daylighting, so that will be exposed to sunlight. So what about UV protection? Is it can that last? Or?
So that drawing is misleading. That earlier kind of drawing, that's really I probably should put a little topsoil layer on that. You would cover that, right? So I'll go back to this slide right here. They put just a thin layer of topsoil on and then they seeded it. And this would be a standard practice in a rural area. The other part is you would drop it into an edge drain or something like that. So yeah, you do want to cover this. We use this in rail and sometimes they just cover it with extra ballast rock. There's, if you can just keep it where it's not exposed to sunlight constantly, then it's going to be fine. So, and you don't need much cover to do this.
Thank you.
Mohammed asked about using an FHWA. That is for another webinar series, I hope, Mohammed. My colleague Daniel there can talk about that in depth way better than I can. I think feel free to reach out to him if you can see Daniel's contact info there. That's the future. We're getting there. So,
Eric, if I can add just one point here about the durability or the lifespan of these kind of products. The oldest material in terms of when it was put in the ground in the Americas is probably about 50 years old. It could be 55, 48, but call it about 50 years old. And some of that material was exhumed. This is about 4 or 5 years ago, I believe, and tested. And the material, and several tests were done. And that material, all the testing that was done for mechanical properties, hydraulic properties, and all that, either met or exceeded the standards that were set back in those days. So to Eric's point, there's very little degradation that happens once the material is in place, within a project.
Well, thank you. We are now just over time. So I think I will wrap us up for today, but thank you so much for the questions, Eric and your colleagues. Thank you for your time and for the information. If anyone needs Eric's contact information after the fact, if you don't remember his email address or didn't grab it, feel free to email me and I can get that to you too.
Hi, Eric. This is Suprasha Reddy. If everybody has something to do, maybe get off the meeting. Need to get off the meeting. Eric, can I talk to you just for a second about the product and how it is used in combination with really like soft subgrade, where we want to use grid along with this wicking geotextile. Have you done that kind of thing before? Have you seen it?
So the short answer is I'm trying to think of a specific project right now, and I can't think of one particular, but I know my colleagues probably do. The first stabilization geosynthetic I showed you, the non-wicking RS580i, that is meant for those soft, wet subgrades, and mechanically it is nearly the same thing as our wicking, our moisture management geosynthetic HRI. So it can provide that mechanical stabilization as well. And it is calibrated to do that under certain design methods. So the short answer is, yeah, it is capable of doing that. You know, my only concerns with that is if it's really severe, and I don't know how much of a concern this really should be, is while it can pull water up, it's only pulling water up 6 inches. So if you do get rutting deeper than 6 inches in a problematic site, would it be able to pull water out of that rut? And ultimately, I think those ruts, given the loading of the overburdened soils, would actually level it out and it still would pull that water out in my mind. But this is just me thinking of how this would work. But it certainly can do it from a mechanical standpoint. And that's, and actually the moisture management, you know, that takes a while for it to move that water. That's not an instant benefit, right? So we need those physical properties for it to succeed in lower CBR soils. And it can do that, right, with the appropriate amount of base and stuff.
Thank you.
Feel free to email me. We can have a Teams call anytime and talk more about it.
Okay, thank you.
Yep.
All right. Well, thank you. I will close us out here, and we hope you join us again next month for the next session. Have a great day, everybody.
Thank you.